So we move on to the structures and properties of individual amino acids. So we start with the classification of amino acids depending on polarity, acidic or basic nature. It's not emphasized in the text yet, but I'd just like to prepare you. Another important classification would be size, among others. The common amino acids have, surprise, surprise, common names. However, as mentioned previously, proteins are considered chains of amino acids bonded to each other. So it would be quite tedious to use the full name every time. So we now present the three-letter abbreviation. Okay, so proteins can be quite long, some hundreds or even thousands of amino acid residues long. So a one-letter abbreviation is also used. You have no choice but to memorize them. Okay, so some are easy, especially if no other amino acid starts with that letter. So you have some have the phonetic basis. So the R, like for arginine, F for phenylalanine, okay, W for tryptophan, tryptophan, D for aspartic acid, okay, Y for tyrosine. Okay, some are arbitrary because there are no other letters left. Okay. Okay, so we'll start with four basic classifications of the amino acids, starting with the non-polar side chains. Okay, so this is really just a shortcut name. It's the side chains that are non-polar, not the whole amino acid. Okay, so these are alanine, valine, leucine, isoleucine, proline, phenylalanine, tryptophan, or tryptophan, I think is the old pronunciation. And then somehow at some point they removed the last letter E. So it's now spelled tryptophan, but supposedly it's supposed to be, it's pronounced tryptophan. But anyway, tryptophan, potato, doesn't really matter. Methionine and glycine. I placed glycine in parentheses because again it's quite small. So some consider that again with the smallness of the side chain for glycine, then the overall structure of the amino acid is polar. So some place glycine in the polar category. Okay, so let's look at the structures. Okay, so we have different representations. You have the ball and stick model, you have the structural representation, and you have the space filling model. Okay, so there are many ways to represent the compounds, no? The chemicals, depends on what you want to emphasize. Okay. So of course, if you draw the ball and stick model, that's quite tedious. So we usually end up using the structural formula. Okay, the one, especially if you look at leucine at the middle of the screen. Okay, so that's probably how we usually write compounds, especially organic compounds. And then just show the the space filling model, which is probably a more accurate representation of how the molecules look like. Okay. Okay, so we have once again in this slide at this point leucine, proline, alanine, and valine. So they're mostly just hydrocarbon chains. So recall from your organic chemistry, alkanes, they don't really do anything. Okay, so here's the next group, methionine. Okay, so methionine is notice it's a thioether. Okay, so sulfur is not quite as electronegative as oxygen. So overall, this molecule is considered as nonpolar. Tryptophan, okay, it's also aromatic. Same with phenylalanine and also isoleucine. Okay, so please start familiarizing yourself, if not memorizing the structures, because they become handy when we discuss a structure and explain the properties of the proteins later on. Okay, so here are the polar amino acids. Please note that alcohol, thiol, and the amide groups, don't forget your organic chemistry. Okay, so serine, threonine, tyrosine, cysteine, glutamine, asparagine, and glycine. So again, here glycine is considered in the electrically neutral polar side chain. As mentioned earlier, hydrogen is not really polar, so some will argue that it should be in group 1 and some in group 2. Again, doesn't really matter. No? What really matters would be its effect in the protein itself, as we will see later. Okay, so we have now serine on the upper right hand corner. So it has the alcohol group. Again, recall alcohols are hydroxyl groups are polar. You have asparagine, which is an amide, glutamine, another amide, threonine, alcohol, cysteine, this is a thiol. Okay, so because you have a sulfur hydrogen bond present, then that makes this polar. And then tyrosine. So if you recall your organic chemistry, it's also a phenol or a phenolic functional group present. And then here are the acidic amino acids. Again, relatively easy because there are only 2. Okay, so you have aspartic acid and glutamic acid. Okay, so aspartic acid is shorter, just one methylene group shorter than glutamic acid, or the other way around. Glutamic acid is one methylene group longer than aspartic acid. And then here are the basic amino acids. Okay, probably the most challenging among the groups because there's not much unity with their structures. So you have histidine, lysine, and arginine. Again, normally I don't ask my students to memorize, but just to understand. But sometimes we cannot get away with it. So you have no choice but to memorize these structures. Do it slowly if you need to. Okay, so lysine, arginine, and histidine. So if you notice again, there's not much unity with their structures. Okay, so here are other ways to classify the amino acids aside from the 4 that was previously presented in the previous slides. Okay, so sometimes it's not enough to just think of them as simply polar, nonpolar, acidic, or basic. So some residues, okay, so we'll define that later, okay, can be called as acyclic. Okay, so that refers to the chain, the aliphatic chain, and it's not cyclic. There's aliphatic chains that also cyclic. Some are aromatic. Okay, some are buried. So what do you mean by buried? Again, later we will, when we talk about the structures of proteins, we will make this a little bit clearer. Cyclic, some are hydrophobic, of course. If they're aliphatic, they're aromatic. Usually they're also hydrophobic. So the size is also important, large, medium. Okay. Now another one, does it carry a negative charge? Is it neutral? Does it carry a positive charge? Okay, polar, again, that's the classical classification of the amino acids. And then as mentioned, the size is also important. Is it small? Is it large? Okay. And then surface. Okay, so again, just like the distinction here is that whether that amino acid residue will be buried or will be found in the surface of a protein. So again, please do not memorize, do not worry too much about this. This will make sense better if we are already studying the structures of proteins.